For our next speaker, we have Kirill Pimenov, Chief Information Security at Parity Technologies. He will talk about the best tools used to accelerate software builds and improve the release process. Welcome, Kirill. I let you take it from here.
Hello. So today I'm going to talk about the tool we build and keep on building for ourselves to speed up our build pipelines, but we hope that in the longer run it will be super useful for everyone and not only for people inside Parity. But most likely you will first notice that it's used inside of our build pipeline. So if you submit some pull requests, hopefully you also submit pull requests to Substrate, fixing our bugs and helping us improve our code, then you will see that the build pipelines are significantly improved. The tool is called Cachepot, and it is currently in the pre-release stage, and hopefully in the next few weeks you will be able to try it out yourself. First of all main development happened to be done by Igor, and I'm only here to present on his behalf for logistical reasons, which means that all the amazing features of the code base are mostly to him, and of course of all other amazing contributors to the project, but all the mistakes and all the mishaps during this presentation are mine and mine only. Yeah, so thank you, Igor. And let's get to it. And you probably seen this, or at least you felt this to some extent. Our Substrate builds are an hour and a half. So when you submit a pull request, you have quite some coffee to drink to make up for that time. And this is not only because our compilation is slow, but it is to big part because the compilation is slow. And everyone who ever builds anything on the Substrate knows that this is one of the fairly painful points of the framework. This is not only Parity's problem. This is fair reasons why Rust compilation is slow, because Rust ecosystem chose correctness and amazing features of the compiler over speed of the builds. But you see that there are quite some reasons why the Rust compilation is slow in general. And unfortunately, we cannot do a lot of features which are inherently slow. I will share the links to the slides after this conversation in the Discord room. Please join it if you don't yet. And you'll be able to click those links and you'll read the amazing posts picking piece by piece what are the main reasons for Rust compilation to be slow. But unfortunately, yeah, our macro-heavy, crate-heavy, highly optimized for the performance of the crypto primitives compilation cannot be made much faster, or can it? And basically, the answer to that is, as usual, caching. And let's start with surveying what are the available caching solutions. And the first and the most basic thing people use when they compile and recompile Rust projects all over is caching target folder. Yeah, this is where all your compiled artifacts live. And this is like a pretty good solution for the single developer developing on their local machine and developing a single project. We all know that there are a lot of idiosyncratic reasons why target folder cannot be shared between projects. It assumes the absolute paths to the compiled artifacts. It is locking itself during the compilation. You cannot just symlink it from one place to another. And to make it even more complicated of a challenge, in our setup with the CI, we cannot always trust that the third parties who are submitting us pull requests are acting in good faith, and they might be using the Rust compiling artifacts to poison our builds. So we cannot just blindly accept the caches from them. This is actually a big and important problem, which is not quite well addressed by half of the tools I have on the screen in the caching solution survey. Because, yeah, after we are done with just caching target folder, the major caching solution on the Rust ecosystem is sccache. It's developed by mostly Mozilla people, and it's actually helps quite a bit. But the problem is indeed what I just said about the security. Rust compilation itself is Turing complete, and the build RS is an arbitrary program which is executed during the compilation phase, which means that if someone can submit a malicious pull request to you, they can execute whatever they want on the builder machine. And sccache basically assumes that whatever compilation unit is doing, they would need a full read-write access to the whole repository of caching artifacts, which is pretty fair assumption if you only build benevolent pull requests. Like, I believe this is what happens inside of Mozilla. Only the already reviewed pull requests are getting to the build stage. But this is not exactly how Parity works and how we interact with our community. Then we looked at the well-known solutions like DC and ICC, which are distributed compilers. And in addition to providing a compilation cache, they provide a very important feature, which is clustering out the compilation. Because, yeah, if a lot of things in our compilation are single-threaded, then by building on the more and faster machines, we can speed it up significantly. Unfortunately, DC and ICC are, as you can clearly see, even from the names, are C compilers, and they're not super useful for us projects. Bazel is something which is in a similar vein from Google, and it's truly a marvel of engineering. Unfortunately, it's a marvel of engineering from a parallel universe. And if you want to build Rust with your Bazel infrastructure, you need to basically cast away all the cargo goodness, and you need to rewrite all the build scripts and all the infrastructure around the project to be Bazel-like. And there are no even decent converters from cargo tunnel to the Bazel manifests. So yeah, Bazel is off the game, because we cannot expect everyone in the ecosystem to learn a new tool just to contribute to our code base. Build Barn is a nice caching infrastructure, which is mostly just that caching infrastructure. And if we are going to build a thing, we might build just borrow some ideas and build it our own. It is not exactly the primitive we want to build. And on the opposite side of the scale, there is a Synchronicity, which is a project by the amazing team at iClusion. And it is very ambitious because it aims not only to create a project local build cache, but it aims to build a global build cache. And for that, in addition to just having sorted out the trusted compilation and clustering out the builds of the intermediary artifacts, you need to solve a lot of problems about the consensus of what are the good artifacts, what are the bad artifacts. And it is really more ambitious than what we need for a project right now. And since when we were surveying the solutions, it was pretty early stage, I would risk saying that it's still at the pretty early stage. So it wasn't something we chose. So we decided to start from sccache and build from it with our own threads model in mind. And like, I don't expect you to read all those tiny letters on this wonderfully designed screen, but in a very broad strokes, the threat model is that, yeah, we might be targeted by hackers, and hackers might submit pull requests which look legitimate, but try to infiltrate our build process and try to poison our caches. And we want our system to stop that out on the design level. We don't want to have any, like, hot fixes and patches to make certain any attack vectors less likely. We want the design which prevents this. Then, yeah, there are operational mistakes. So we don't want that to cost us $30,000 in a monthly bill just because there is an infinite loop in calculation, and we just have to pay all the servers Google was able to provide us in a short amount of time. We want it to be reliable. We want it to be really easy to deploy and operate and monitor. Then, yeah, we definitely don't want to be targeted by someone who just discovered, oh, there is an open Redis port that's like, so suck out all the data you have in there, or like replace it with a picture of kittens or something like that. So basically, it should be some decent level of network exposed, secure networks daemon. And then there are a couple of items in our threat model, which I wouldn't call out here because they're pretty specific to Parity and pretty specific to the way we protect our infrastructure, but they're in the same vein with everything else. To solve those issues in our threat model, there is always exists a security model. Like, threat model is a riddle, security model is the answer. And our answer is pretty straightforward. We use the well-known encrypted network communication protocols. We use the well-known authentication protocols. We are capping all the execution, all the work queues. So there is no infinite loops, runaway builds, or something like that. We don't trust the third-party blobs. We don't trust even third-party code, and we either cross-verify or build in trusted, isolated environments. We should make Cachepot really simple to deploy and maintain, which is like frequently overlooked in the age of Kubernetes, but this is still a design goal for us to make it easily operatable in a wide variety of environments. And it should be easily monitored, which is in the modern world probably mean we have Prometheus metrics. And Cachepot is all of that. And the main answer we had to give is that unfortunately we cannot have fully deterministic builds of our compilation units, of our crates, of our dependencies, and so on in the Rust dependency tree. We cannot have that because Rust relies a lot on the C libraries. It is really hard to make C libraries build deterministically in a Rust compilation and linking context and so on. But we can sort of work that around, and this is why I call them deterministic with quotation marks. We basically can assume that our compilation results are reusable, meaning that whatever we came up with from the same code base, from the same set of inputs, let's say compilation flags or system dependencies or the Rust compilation version and the target, and we identified most of the things which affect the results. So as soon as all those inputs are fixed, it is safe to reuse the previous compilation result. And this is the key thing which Cachepot is doing. It analyzes your build and it stores the compilation results in a key value store under the keys which are hashes of all those possible build inputs. And those build inputs are then change if anyone submits something malicious to us. So for example, if someone tweaks the build flags to make an artifact build something we don't want, it will be built and it will be put in cache, but that cache will never be used by anyone who is not explicitly asking for this particular configuration of the unsafe build flags. So we don't worry about that. It doesn't poison the whole cache we run. And provided that we containerize our build nodes enough, it is not going to be a security issue for us. And this is, here comes the architecture. And once again, this is a pretty detailed slide. I don't expect anyone to study with magnifying glass right now. But the idea is that we have a properly easy to deduce distributed compilation farm with a cache setup. There is a coordinator, and your cargo build offloads the builds to the scheduler. Then we have a farm of the compilation units, and they build things in a controlled environments with a sandboxed sort of container, even if it's not actually a Docker container, it's a little bit more than that. And the results of those compilation units are put in the cache on predefined keys, and cache is access controlled. So basically our compilation sandboxes cannot access and override arbitrary cache limits, which is crucial in a setup like this. And yeah, unfortunately, this model is not fully compatible with what we have in sccache. And because of that, we decided that we try to upstream as much of the changes as possible to the project, and we can try to contribute as much. We try to contribute our updates of the dependencies to use the latest Docker version everywhere throughout the sccache code base and things like that. But at a certain point, it just became clear for us that sccache has its own goals, and it's going to be that cozy, trusted environment thing, which is much less overhead in terms of the code base, in terms of maintaining all that security and bookkeeping and hashing the inputs. But for us, we just decided, yeah, it's going to be a Cachepot, and we will be very open that it's forked from sccache, but it's not sccache anymore. And this is why the new name and that fancy logo. Thank you, Sveta. Yeah, numbers. You all wanted to hear numbers. Unfortunately, they are preliminary, meaning that this is not the final release, and we still working out some quirks, but it can build Substrate. And if you ever build Substrate, you know that this is quite a fit. The Substrate imports all the possible libraries in the ecosystem. It imports all the possible dependencies. It wraps some C crates, and it requires things like RocksDB, which is by itself a pain to compile. And honestly, to my surprise, build with a Cachepot is faster than a regular cargo build when run on a single machine. And like those numbers are just compiled by running the Substrate build on a laptop and running the Cachepot scheduler on the same machine and running the Cachepot build farm on the same machine and running the cache on the same machine, which sort of assumes quite a bit of a networking overhead on just a regular developer's laptop, which is like nice machine, but like not something stellar, not something like a cluster of like top tier server CPU nodes. And even with that, and even with all the overhead, we see certain speed ups in the compilation. But most importantly, there is a column which I call incremental, like rather unluckily. I would bet I should have better called that build with a warmed up cache. And you see that when we have cache and when we just change something in our main Substrate code base and we try to rebuild, that our first of all, savings are real and savings are there. And yeah, once again, Cachepot wins over the regular cargo build on the same machine using the local cache, which is rather surprising and probably highlights that Cachepot is a marvel of engineering. Let's build Polkadot with a warm cache and let's see how much it saves. Yep, I was a little bit wrong about marvel of engineering, right? And this is basically the main caveat right now, and this is why you don't see Cachepot used in our public build pipelines yet. We still struggle with certain advanced C compiler wrappings, and because of that, we cannot build Polkadot right now. The work is underway to make all of that fixed, and actually there's been some significant improvements throughout, like me even coming up with those slides, but still, the problem is that to build Polkadot, you need gmalloc, and gmalloc assumes autotools, and autotools is basically a glorified set of bash scripts, which absolutely stagger when they see that your C compiler is wrapped in some sort of a Cachepot thing. We disabled gmalloc. This is not the way we want our Polkadot code base to run in production, but for the sake of this, we disabled it. And with a pre-populated cache from Substrate, but no previous Polkadot builds, we build in 25 minutes, which is, I believe, if you ever try to build Polkadot, you know how much of a time saving even 25 minutes are. And most importantly, the cache with a proper build of the Cachepot and the proper deployment of the Cachepot would not only be shared between different projects and between different nodes in your build pipeline, but at the same time, you can use the same compilation farm to empower your developers. So instead of compiling on the MacBooks or whatever other desktop-grade hardware they use, they can all be reusing the same build artifacts built on a very powerful cloud machines, which are already powering your build pipelines. And because of most of the dependencies in their development copies would be shared, there will be like significant time savings in this setup as well. So we hope that when Polkadot is compiled successfully without modifications on Cachepot in a few weeks, fingers crossed, it will be a really, really useful project for anyone who works professionally with Substrate-based chains, with Polkadot, with other runtimes. So yeah, it's somewhat usable. It can finally compile Substrate. That was a huge win because this is where most of the C magic happens in compiling all the Polkadot code base. It still struggles with C build tools here and there, you know, and two major caveats. And this is why I said that incremental as a name for the column is rather unlikely. Rust supports incremental compilation, but unfortunately Cachepot doesn't. And we have some plans to do that, but for now, every build is assumed to be a full build. And if you set up the incremental compilation flag to your Rust compiler when building your artifacts, basically Cachepot says, oh, none can do, and here are your artifacts, please incrementally build them yourself. And that implies a lot of network bandwidth and probably worse performance than if you would be building that on the remote distributed cluster. So yeah, no incremental compilation supported yet. And our linking support is not stellar either. it is somewhat in the works, but generally, yeah, if you need to link something complicated, it will be the same. Oh, I'm a Cachepot, I don't have no idea how to do that. Here are your like pre-linked artifacts, please do that yourself. And this is actually would be a big challenge for us, but also something we really, really like to solve, because linking and especially link time optimizations are a big source of performance gains in Rust codes. And at the same time, linking by default is very, very CPU bound and single threaded. There are some alternative linkers which try to imply multi-threadedness, but they are not yet ready to compile the project as big as Polkadot yet. So we need to do more R&D here. And when linking is done and we can build all the possible C tools with outer tools, then Cachepot will be release 1.0. Yeah, what's next? Remember that synchronicity project? We really like to join efforts somehow. We really like to see that Cachepot evolves in the same direction and enable some global compilation cache, because it makes very little sense for multiple projects to compile the same code base, like the same dependency trees of the Rust artifacts with fixed versions over and over, just to build, here we build the Polkadot runtime, here we build something else which is on the same version of Substrate. That's just wasteful. And we already have amazing projects like IPFS to store and share those artifacts globally in a verified manner. But basically, it is not the complicated part. As I already mentioned, the most complicated part here would be some sort of the reputation mechanism or verified compilation mechanism, because anyone can submit anything to that compilation cache. And some of those anyones would definitely have malicious intent out of either monetary interest in backdooring some cryptocurrency project, or just out of the sheer fun of setting world on fire. So we need to figure out how to do that in a safe way on a global scale. And if we do, basically not only Parity's builds would become much faster, but everyone else in the global Rust ecosystem would benefit from this. Yeah, so that's Cachepot, and thank you. And now it's time for questions.
Okay, thank you, Kirill. That was really great talk. I mean, many times we don't really think about all the possible security issues that we could introduce while we do the builds, but yeah, it's really good to know all these options. So we have a few questions from the audience. So I think you already partially answered this one, like it says Substrate compiles many dependencies in parallel, but at the end, the whole compilation slows down to one process. Is there something that can be done to just improve the whole process, and probably it's related to the linking stage?
There are a couple of multi-threaded linkers, and if they will become mature enough, we'll be the first ones to try them out. There are some other reasons why certain things in Rust are single-threaded, and as far as I know, the Rust compilation team are trying their amazing best to solve this and to make all the CPU-constrained single-threaded things as parallel as possible. Thanks to Rust, that's really delightful to do, thanks to the fearless concurrency enforced by the Rust compiler primitives, Rust language primitives. But still, some things cannot be solved other than linearly, and there is not much we can do other than throwing the most powerful CPU we have in house to do that stage of the process.
Okay, yeah, thank you. I think that's probably something I have also seen, like when we do the builds, and makes total sense that we should explore.
Important thing to avoid doing that on the developer laptop, right? This is not the CPU you have the most powerful in the house. And
that's true. That's also true, yeah.
Even internally in Parity, we have a special machine which developers who are not plugged into the wall sockets can use using the amazing tool which is called Cargo Remote, which also inspired sccache fork and Cachepot a bit. So you build things on the remote machine, which has a really powerful CPU, and people see savings even if they have to pay the network transaction costs to upload things there, compile it there, and download it back. So sometimes, yeah, just having a more beefy CPU is everything which matters. And with Cachepot, you can plug in the build farm of the most powerful CPUs you can afford.
Okay, great. So related also to that, like there's a question asking if Cachepot downloads the cache from the network.
Yes, it's all networked, so you can have multiple components. I don't think it will make us much good if I will scroll back to the architecture diagram, but basically you have three types of components. It's like scheduler, it's cache storage, and those are actual compilation builds. And all of them are networking together. So there is no way around that. You have to pay the networking costs, but this is basically the price we have to pay for another requirements of ours, which is like robustness and easiness to deploy. So no matter if you deploy it all on the same machine or you deploy it on a cluster somewhere in Kubernetes or whatever your fantasy suggests you to do, you still have all those authenticate and communicate through the network. If you do that inside of a data center, for example, then those network accesses sometimes are cheaper than accessing the local disk. So this is not a huge bottleneck for our performance.
Okay, great. Thanks for that really good answer. So yeah, there's also another question. I mean, I think it's kind of obvious that I think it doesn't work directly on Mac right now. It's more like Linux.
It is not in our very short-term goal, because like speeding up the builds in our build pipeline is like the more lowest hanging watermelon we can pick. But generally, there is like cross compilation in Rust is actually quite nice. And it is absolutely within the architecture that we will be able to cross-compile to Mac. Like you will still be doing the actual compilation on whatever the machines you are using, which is like most likely Linux, like 99.9% of the chance. But you will, with very little effort, make it compile the artifacts which are usable by Macs. And if I understand correctly, both Intel and M1 Macs would be supported. And basically, this is yet another input to that hashing mechanism, which hashes the deterministic set of inputs into the key for the key value store. So basically, all the Mac builds will be just occupying the separate set of cells in the storage key value cache. And that's it.
Great. So we still have time for one last question. So this is just, I think it's from Yoshi. He's asking like, yeah, using the cache is faster even for a clean build. So is that statically significant result?
Don't know, because like distributed systems are like really, really hard to trace and profile properly. But we see then that from time to time, it's a little bit surprising. And our current belief is this is mostly due to Rust not in a single cargo run, not doing the best job, or not being supported by the OS that great in splitting the tasks through the CPUs. So when you have separate compilation units running in isolated containers, which occupy and pin to the different CPU cores, you might squeeze a little bit of the precious CPU performance during the compilation, even if you have all the overhead of splitting the work. But this is like a very, writing in the air sort of level of analytics. We don't know for sure.
Great. Thank you so much, Kirill. This was really great answers.